So as I mentioned in my introduction, we are going to be writing a single function called image styler. And what that function is going to do is it's going to take an image and it's going to apply some styles to it. So it can either be things like blur, sharpen, RGB. We're going to be changing the colors of an image. But the idea is that we're going to be defining our own custom function and we are going to give it some image styling capabilities. So when the function is done, this is what it's going to look like. So we are going to be using, throughout the webinar, we're going to be using this test image of a house that's built into the Wolfram language. If you're not familiar with this example data, that's a built-in function in Wolfram language that has, well, as the name suggests, it has a lot of example data built into it. In this case, we're going to be using image, but this example data function is very useful if you're experimenting, if you're learning something new in Wolfram language, and you just need some data set to play around with. So there are images, there are sounds, there's all sorts of data, videos, there's databases, yeah, pretty much everything that you might be learning in Wolfram language. There is probably some example data, so you can focus on the concepts themselves rather than, let's say you're learning something related to databases. You don't have to go on the web and look for some example databases and import them in Wolfram language. So example data makes that much easier. And that's why we're using it in this webinar. So yeah, you'll be seeing this little house quite a lot in today's webinar. But once our function is finished, this is what it's going to do. So here we are calling, well, you don't need to worry about the way we are calling it. We'll get into that a bit later on. But we're passing it our test image and we're passing it some arguments like blur, sharpen, RGB. We'll be able to pass it options as well. So if we are defining blur, for example, we can define the radius of the blur. If we are doing sharpen, likewise, we can specify the radius of the sharpen effect. RGB values, so we can multiply the different color channels by some factor. So in this example, we're multiplying the red by 3, we're multiplying the green by 2, we're leaving the blue on its own. And this is what that looks like. So yeah, we are going to pack quite a lot of functionality into our little custom function. And once it's done, this is what it's going to look like. Oh yeah, we can do grayscale, we can resize the image. And equally as important, our function is going to be able to handle bad input. So as you see in the previous times that we call the function, we are passing things that the function already knows how to do. But obviously, especially if you're writing a function that's going to be used by other people, you need to be able to handle bad input gracefully, so to speak. Instead of just erroring out, you can provide informative error message. So if someone tries to call the image styler function with something that is not an image, in this case, just some undefined symbol in Wolfram language, you can give them an error message saying that this is not an image. If they try to call it with an extra argument, you can give them an appropriate error message for that, and so on and so on. So this is what we're aiming for, and this is what we'll get at the end of the webinar. So let's actually get into it. Something I forgot to mention during my introduction is that if you have any questions during the webinar, I'm keeping an eye on the Big Marker chat, the Q&A tab on Big Marker. And I'm also keeping an eye on the YouTube live chat. So yeah, any questions during the webinar, feel free to drop a message, and I'll probably I'll find an appropriate time to respond to it, either during the webinar, or if it's kind of more complicated, I'll probably leave it towards the end. But yeah, let's get into the content. So we're clearing all the definitions of our function, so we can start building it from scratch. And before we even start doing that, let's take a step back even further and talk about functions in Wolfram language in general. So what is a function? Functions really are the backbone of any code or any project, any workflow that you're engaged in Wolfram language. And already when you start using Mathematica, there are thousands of functions available to you that you don't need to define yourself. You can just call them by their name. You can pass them some argument and use them. Even though there are thousands of functions, obviously there's more than, and there's hundreds of thousands of things you might do. So whenever you want to do something that is not explicitly defined as a built-in function in Wolfram language, that is when you define your own function. So that's the basic idea of what functions are and why you might want to use them. So let's actually look at the syntax, first of all, into how we actually define our functions. So this is kind of the very basic function definition. So let's look at it step by step or element by element to see what it is composed of. So first we start with our function name. So in this case, we are calling our function image styler. Now that name can be pretty much anything. So you can have normal letters. You can have numbers. There are some limitations. Like I think your function can't start with a number. It can't include some things like operators, like this or this. But other than a few exceptions, you can have pretty much anything in the function name. You can have obviously letters from the Latin alphabet. You can have different scripts. You can have basically any Unicode characters. So you can have things like emojis in your function names if you want. Yeah, there are very few restrictions. Typically, function names follow this convention, this kind of camel case. I think it's called convention, where if there are multiple words, the first word is lowercase, then the second word starts with a capital letter. But you're very free to kind of choose your own name for the functions. So after the name, what we have is the arguments, which are in square brackets right after the name. So as you can see, so the brackets contain comma-separated arguments. So as you can see with our image styler function, we start with two arguments. One is called image and one is called style. Now you'll notice that after each argument, there is this underscore. And we are going to be talking about this underscore and the things that come after it quite a bit in this webinar. But the underscore stands for a pattern test. And in this case, so the underscore itself means any Wolfram language expression. In practical terms, that means that the image argument can be of any type. It can be an image, obviously, but it can also be a number. It can be a string. It can be an audio file. It can be a video. It can be anything. If you want to restrict it to only being an image, well, we'll get into that very shortly. But for our very basic definition, we are saying that we have two arguments called image and style, and those two arguments can be of any type of Wolfram language expression. So once we're done with our arguments, we close our square bracket, and we have this set delayed, I believe is the Wolfram language term for this symbol. And that's just the definition of your function, sometimes known as the walrus operator, affectionately in some other languages. And then on the right-hand side of your set delayed or your walrus operator, you have your actual function definition. So what is the function actually going to do? And in the case of our image styler function, the basic definition is it takes image and it wraps it into some style. So if the user provides blur here, then blur is going to be inserted on the image itself. So fairly simple idea. Okay, so let's start actually expanding on our basic function definition. So what you see here is a very basic way in which we can do something different depending on what the user input is. So let's go through the actual function, the actual functional part of the function. So the highlighted on your screen. And we are saying now, again, we have an image. Now we use this switch statement, and switch statements are very similar to if statements, so they do different things depending on what the value of something is. So in this case, we are checking the value of style, so style being the second argument in our function. So we are saying if style is blur, is this string called blur, then do this. This is, so let me try to rephrase that. If the argument of style is blur, then apply the blur function to the image. If the argument of style is sharpen, then apply the sharpen function to the image. If it's RGB, then apply the RGB function. If it is anything else, again, reminder that this underscore in Wolfram language, I think it's called a blank technically, but it stands for any Wolfram language expression. So we're saying if the style is one of these, then do their kind of corresponding functionality. If it is anything else, anything other than blur or sharpen or RGB, then just return the image. Don't do any styling to it. Now, the important thing to notice here is that these blur function, sharpen function, RGB function are not actually defined at this point. So at this point, we are just kind of we're mostly concerned with the architecture of our function, if you will, because once we have that right, then we can actually define these functions, and they can be used in our image styler function. So yeah, that's another very common pattern. Instead of having one humongous function doing a lot of different things, it's often a very good idea to kind of break up different functions and call them from each other. It just keeps things more modularized, more maintainable, more readable, just nicer to work with. You can, of course, also have a function that calls itself, which is more commonly known as recursive functions and things like that. I think we cover some recursive functions, recursive functionality later on, so maybe we'll get to that. But that's the basic idea. So we're starting to kind of build the logic inside our function. Cool. So as I mentioned, because we haven't actually defined our functions here, our function is not going to do anything yet. But we'll get to that a bit later on. Cool. So to implement these styles that we want our image styler function to do, we're going to define some helper function. So for some of the things that we want our image styler function to do, they're already built in Wolfram language functionality that does that. So we can just reuse that in our own function. So just like I mentioned that we can call our custom defined functions from all our custom defined functions. Obviously, we can call Wolfram language functions from our custom defined functions as well, which is what we are going to be doing. So for the blurring effect, there is already a Wolfram language function called blur, which takes an image and a radius, and it applies the blur effect to that radius. And likewise for sharpen, there's also a built-in function for that. For the RGB style, however, we need to create our own function. So let's define this, and let's look at what it's doing. So here we have another function called RGB style, which takes two arguments. Technically two arguments, but we'll get into what this is. So the first argument again is the image, and the second argument is a list of values, R, G, and B. Obviously the factor by which to multiply the red channel, the green channel, and the blue channel. And again, at this moment in time, we're not restricting them by anything. We have these blanks, so these could be anything. And obviously, this is going to work if the image we pass is actually an image. But at the moment, our functions, because it's not restricting anything, as a user, we can pass a number for this argument, and that's going to cause all sorts of errors downstream, but we'll handle those a bit later on. But anyway, our RGB style helper function is going to separate the color channels of an image, and it's going to multiply them by the values that the user provides. So let's define that and let's test it. So you can see that here we're calling our helper function, we're using the test image of our house, and we're passing a list of factors by which to multiply the channels in the image. So we're saying multiply the red channel by 3, the blue channel, the green channel by 2, and leave the blue channel as it is, or multiply it by 1, which is the same thing. So this can be any other value, obviously, and that's going to work as well. So let's build, now that we have, so again, just to remind ourselves, we want our function to be able to apply the blur effect, the sharpen effect, and the RGB style effect. Well, for blur and sharpen, we already have the built-in functions. For RGB style, we defined our own. So let's plug that into our image styler function, and this is what it looks like. So this is the same as we had it previously, but now instead of an undefined function, we are using the built-in blur function, sharpen, and our new RGB style function. Cool. So just with that, now we have a functional function. So we have a function that actually does something now, and we can actually test it. So we can. So here we're calling the function 3 times with different arguments. The first time we're calling it, we're passing it the test image, and we are passing it the string blur as a second argument. Let's go back to our function definition and see. Let's kind of retrace step by step what happens when we call this function. So we're calling it. We are giving it the test image, and we're giving it the string blur. So we go into our definition. We know we're going to return an image. We have this switch statement on the style argument. We're basically asking what is contained in the style argument. If it is blur, which in this case it is, then this piece of functionality is executed. The blur function on the image with radius 10. So once this is executed, none of the other branches of the switch statement are evaluated. We just get the result of this statement. Similarly, the second time we call it with sharpen, only this branch of the switch statement is executed, and we get a sharpened house. And the third calling of the function, we just have RGB, which calls our function with some default values. So at the moment it's functional, but you notice that we are hard coding some of the things inside the function. So we are saying that the blur is always going to be with radius of 10, which is obviously not, it's functional, but ideally we want to be able to allow our users to specify their own radius, and this is what we'll do when we get into options. But yeah, so a very basic functional function in Wolfram language. And the other thing that it doesn't do yet is handle bad input gracefully. So let's look at here. We're calling the function twice. So the first time we're providing a valid image, but we're providing a bad style. Now our function actually is able to deal with that fairly reasonably. And let's look at why is that. So if we go back to our definition, when we provide a bad style, a style that doesn't match any of our blur, sharpen, or RGB, it actually matches this blank underscore, which again stands for any Wolfram language expression. And because bad style, even though it's undefined, it's technically a Wolfram language expression. So it matches this blank. Which means that the function just returns the image as it is without applying any styling to it. So you can think of that as a kind of a reasonable fallback or reasonable default. But if we do something else, like try to pass an image that is not an image, we get actually fairly reasonable errors. And these errors come not from our own function, but from the in this case from the blur function and from the image function, which are built-in functions in Wolfram language. But there you go. We'll be able to handle that later on as well. Cool. So before I get into arguments, I would like again to take a step back and just talk about different ways of accomplishing the same thing. So the problem is, how do we handle bad input? How do we handle input that our function is not designed to work with? one way you might think of immediately is to add some error statements. So for example, here we're switching on style, and instead of catching everything with this blank, maybe we want to catch some specific style and print something out saying, hey, our function doesn't support this, please provide one of those styles. So that's one way of kind of handling bad input. But another way of doing the same thing is to define our function only for specific types of arguments, only for specific input. And the advantage of that is that if the user tries to provide any arguments that our function doesn't accept, then we don't even need to go into the actual evaluation of the function. We can stop very early and say, hey, your arguments, so there is no function for the arguments you're providing, which is usually a cleaner way to handle bad input. So that's kind of the engineering perspective on it, if you like. So let's see how we can actually accomplish that with syntax. What does the syntax for that look like in Wolfram language? This is our new function, and as you can see, it's exactly the same. The right hand side is exactly the same as our previous definition, but here we have changed the arguments. So let's look at what we have done here. So again, we have two arguments, image and style. This time, instead of each argument having only blank after it, we define the head that this argument should be. So what do we mean by the head? So every Wolfram language expression has a head. Now you can think of the head as the type of the expression. So when we have some text, the head of that is string. If we have some number, it's integer. If we have some decimal number, it's real probably, and so on and so on. If we have a list, then the head is list. If we have an image, obviously it's an image. So we can use the head of each Wolfram language expression in our function definition. So in this case, if I delete all of this, in this case, we are saying that our image argument, the first argument, should have the head of image. Our second argument, style, should have the head of string. So that's really all it takes to restrict the arguments that the user can pass into your function. And that's already very helpful. So you might be wondering what happens if we define our function like that. What happens if a user passes an image that doesn't have a head of image? And the answer to that is that the function is simply not going to be defined. So let me show you what I mean by that. So let's pass some number, which is obviously not an image. Let's say blur. So what happens in that case is the function returns itself, which is basically the Wolfram language way of saying that the function is not defined, or that function doesn't exist. So even though there is a function called image styler, there is no function called image styler that takes an integer as its first argument. So again, this is kind of a very clean way of not even having to go into the right hand side of the function and trying to pass this number to the blur function as an image and getting an error from that. So here again, this is our Wolfram language way of saying this function doesn't exist. The function to apply blur to an integer doesn't exist. Cool. So yeah, so there are actually a few ways of restricting arguments, and they all try to accomplish the same thing. They all try to make sure that whatever input, whatever arguments are passed into your function can actually handle. So restricting by the head of the expression that go into the arguments is probably the most simple way. But you have other ways. Mainly we'll be covering restricting by head, which is what we're doing here. We'll cover restricting by predicates, which is going to be our next example, and we'll have restricting by conditions a bit later on. They're just different ways of accomplishing the same thing, just different levels of complexity as well. While head is very simple, um, it's not very powerful in the sense that okay, we're saying that style can be string, but obviously it couldn't be any arbitrary string. It has to be one of blur, sharpen, RGB. So we'll get into more complex ways of restricting our arguments, but for the sake of simplicity, this can get you a long way. Restricting by heads can really add a lot of power to your functions. So hopefully that is clear before I go into predicates. And if it's not, let me know in the chat. I don't mind at all going back and explaining it in a different way and things like that. Cool. So let's go back into one of our helper functions, RGB style. And if you remember with RGB styles, with the RGB style helper function, we are accepting an image, which now we can have the head of, we can require the head of that image argument to be image, just like in our main function. And we are also accepting a list of 3 values, so the factors by which to multiply the red, green, and blue channels in the image. Now, we could say that each of these values should be a real number, for example, or an integer. But what if we want to be more specific? What if we want to be what if we want to say that not only should they be integers, but they should be positive numbers? There isn't a special head for positive numbers. So if I go back and kind of give you some example, for example, head of 5 and head of -5 have the same head, which is integer. So if we only want to take positive numbers, we couldn't do that just by restricting by head, and that's why we need that. That's where we need more complicated tests, and that's where predicates come into play. So let's look at how we do that. So have our RGB style, have our image argument. For RGB values, we have the name of the argument, and now we have a colon. Actually, before I go into this part, let me just show you what the colon does. So if you have a function of x that does something that returns x, let's say, this syntax, this x blank or x underscore, is actually a shorthand for x colon blank. So when you can spell it out with x colon, but if you just have a simple argument, a simple expression, simple head to match, you can just have the underscore right after the name of the argument. But in this case, because we have a more complicated pattern than just a head, we are using the full colon notation to signify that. So we are saying here we are saying that RGB values should match a list. So here we're starting a list, and the list should contain the list should have 3 positive numbers. To say that in plain English, but let's go into the syntax word by word. So we use repeated, which is a built-in Wolfram language function, and here we have a test. So what we are testing for is whether each of the numbers matches this positive number q. And what positive number q, or posnum q, is another custom defined helper function, which takes an expression and it checks whether both of these conditions are true for that expression. So it checks whether it is numeric, and it checks whether it is greater than 0, obviously. So we can call this function now with some numbers so we can test it. Posnum q. So you can see that now with our helper function, we can actually distinguish between positive integers and negative ones, and we can return true or false. And this is really all we need for now, because we want to say that RGB values should only be valid if all 3 numbers return true for this positive number q function. So the syntax gets a bit more involved here, but the idea is still fairly simple, I believe. So we are just running slightly more complicated test on our arguments. And then the right hand side is still the same. So, but now importantly, the right hand side is not even evaluated if the factors of RGB values are not positive integers. Cool. Let's define that and let's test. So again, now we are able to handle bad style again. And as I mentioned, when a function returns itself in Wolfram language, that basically means that it's not defined or unevaluated. So the next thing we can do is we can provide some default values. I mentioned in the previous example that when you have this colon, you can use that for the pattern. However, you can also use it to provide default values. So this is where the syntax gets slightly obscure. So if you have this, if I return to the original definition of the language, so here we're applying the head restriction without using a colon, which means that anything after that, any colon after that, is going to define a default value. We can do we can do this as well, which is pretty much the same thing. But if you see two colons in a argument definition, that means that everything that comes after the second colon is the default value. So let's define this. And the idea here is we can have some dummy value, which is going to be called by this this blank branch in our switch statement, which is going to return the image. But again, we can be that's a bit of a hack, and we can be a bit more intelligent with our restrictions. So again, we're going to be using this predicate test for our style argument. And one thing I should have mentioned probably, and I forgot. So everything, this special syntax, blank question mark, everything that comes after the question mark, you could have any piece of Wolfram language code that returns true or false. So anything that returns a Boolean value can come after the question mark. And if whatever comes after that returns true, then the function is valid. If that thing returns false, then the function is undefined. So we have a lot of any Wolfram language function that ends in capital Q, like numeric Q or string Q, or there are even things like I think daylight Q, which is interesting. And daylight Q basically tells you whether, based on your location, is the sun out or not. So it's downloading some astronomy data to determine whether the sun is out on my location or not. So, but basically, any you can use any of the built-in Q functions in Wolfram language to test whether the argument returns true or not. Again, if it returns true, the function is valid. If it returns false, it's not. Or you can have you can define your own custom predicate functions. So you can define functions that return true or false, and you can use them just the same way in this kind of predicate test, which is actually what we did with, if I go back to the previous slide, when we defined our pos num q function, our function only ever returns true or false. So again, that's why we were able to use it here again after the blank question mark. Cool. So let's look at, so what we are doing here is we are matching whether something is a string. If it's not, we're assigning it to automatic, and then we're providing a default value as well. So a default value, again, a word on some default values, or a word on the role of default values in functions. So in many cases, you might want to provide a default value for a function, especially if you're using built-in Wolfram language functionality in your custom function. A lot of the options can take this automatic value, and what that means, what that means depends on which function you're using, obviously. But a lot of times this is just a reasonable default. So it's it either applies some heuristics, or it just takes a reasonable default value for that function. So here we are saying that if the user doesn't provide any style, just use automatic. Cool. So, and again, we can do that with our custom RGB values argument. We can provide default values if the user doesn't provide anything. So we can say we can give it a list of 1, 1, and 1 as default values. And what that means, obviously, is that the image is going to be unchanged because each channel is going to be multiplied by 1, leaving it essentially the same. So you can think of it as a kind of a safe fallback. And what this means, the main value, the main utility of providing default values is that the user doesn't need to specify them if they don't want to. So now, even though, so let's look at this first line where we'll call the function for the first time. We're just passing it an image now. We are not providing anything for style. And because style now has a default value, which is automatic, and because our RGB style function has default values for this, then we can safely return the image itself. If we didn't have default values and we tried to call only with the image, we would get an unevaluated function. Again, this is the Wolfram language way of saying, of telling us a function that only takes an image doesn't exist, is not defined. But now it is, because we have a function that takes an image and it also has some default values. Cool. And yeah, likewise with RGB style, because we have default values now. If we call RGB style just with the image without providing the factors by which to multiply, we get the image back as it is, or each channel multiplied by 1. And if we want to provide the values explicitly, we can do that as well. And that is actually, so just before I move on to the next slide, a few more things to say about default values actually. The idea of default values that don't need to be specified runs actually quite deep in Wolfram language. So especially if you're dealing with kind of functions that do a lot of things. So for example, classify is one such function. Classify takes some data and builds a machine learning classifier based on that data. So in the most basic case, you can just provide the data to classify. So let's say we had some data, you can provide the data to classify and you can actually run it. Well, at the moment I'm passing it blank expression or undefined expression, so it's not doing anything. But if I had some data, I can pass it to classify, and that's all I need to do. And I'm going to get some machine learning classifier out. Now, of course, classify can actually take a lot of different arguments, a lot of different options. But the idea behind, and the idea is that all of those different arguments and different options can have a default value or can have a default value of automatic. So for the end user, as far as the end user is concerned, they can just pass in their data. If they're not interested in any of the other options, they don't even need to see them. They don't even need to concern themselves with them. They don't need to do their own research into, what is a sensible default method I can use with this type of data. They can just pass in their data and Wolfram language can figure out not the ideal, not the perfect option for each argument, but it can figure out sensible defaults. And this is essentially what, we're working with a very simple function, of course, but we are kind of emulating that philosophy that arguments, unless they're explicitly necessary, like with the classify function, obviously you need to have some data to run a classifier on. It's impossible for the function to run without data. But for things like methods and different parameters of those methods, yes, if you're a user who is interested in providing every single value to every single argument, you can do so. But if you are somebody who is just playing around with their data or they're exploring machine learning, you should be able to get started simply by providing your data. And you get out a machine learning model on the back end of it. And once you have experimented with your data, once you're comfortable with the function, that's when you can go deeper, and that's when you can obviously read the documentation and provide your values. So, okay, let's keep moving. Options. So before I go into options, let me just scroll back just to see, because I think something is missing here. Oh, okay, so it is here. So I mentioned that after this predicate testing, after the blank question mark, you can have any Wolfram language expression that returns either true or false. One thing I wanted to mention is that that expression, it can be a basic function like match q, string q, numeric q, daylight q. So you can have a function that only works during daytime, for example. That's an interesting idea. But this expression can be more than a simple predicate function. It can be a whole pure function, which is the case here. Now, in this case, it's a bit unnecessary. So hopefully, actually, probably let's look at. I'll open a new notebook, and I will write some example on the fly, because this is quite an important idea, and it's very useful. So I don't want to gloss over it. So let's define our own custom function for this demo. Let's say reverser function. And our function is going to take one argument, which is going to be string, our walrus operator, and we will apply, what is the function called? String reverse of x. So very simple function, takes one argument and does one thing to it. So if you call it with A, B, C, D, E, what it does, it just reverses the order of the letters. So here, as you can see, we are restricting by string, which is very useful, because if we call this by some number, it's going to refuse to do anything. So that's already very useful. But let's say we have some more conditions. We have some kind of filtering logic for our argument, and in this case, it might be something like so we have our question mark, which is going to evaluate basically everything that comes after the question mark and see whether it's true or false. So whatever we write here, and the parentheses are not strictly necessary, but when you're writing pure functions, especially in function definitions and things like that, they can help a lot with the scoping. So the test we can have here is something like, let's say string length of our argument is longer than 5, for example. So here what we are saying is that not only our argument needs to be a string, but it needs to be of length greater than 5. So let's test that. Clear or reverse function. Okay. So now if we run our function with a very short string, this is exactly 5, but let's say ABE. If we run that function, then it's not going to be defined because it fails to match this pure function. Or another way to say it is that this pure function returns false for this argument, which is why it fails this question mark test, which makes the whole function undefined. The reason why I wanted to spend a few extra minutes on this is that this is an extremely powerful way of restricting your arguments. So not just with match q and numeric q, but with your own custom logic defined as pure functions after the question mark, you can pretty much do 90% of any type of restriction you want to do just with this this simple syntax and this simple logic. That's why I wanted to touch on it a little bit. And actually, I'll leave this notebook open. Maybe sometimes it's useful to take a step back from the big function we're building in the webinar and just take a more simple one to illustrate some concepts. So I'll leave that minimized, and we'll go ahead, see if we come back to it. So options. So the next thing we want to be able to do is, other than arguments, we also want to pass options. And the reason to do that is, well, in the context of our image styler function, maybe we want to allow people, instead of hard coding the radius of blur, for example, as 10, we can allow the users of our function to specify whatever they want the radius to be. So the idea behind options itself is very simple. The Wolfram language syntax for adding options to your functions is a bit, in my opinion, is a bit obscure. So let's, well, not obscure, but it feels kind of heavy. It feels a bit complicated, especially if you're just starting out. So let's break it down. Let's spend a few minutes on options as well before we move on. So the first thing you need to do is to call the options, which is a built-in function in Wolfram language, and the argument that function takes is your function, so the function you want to define options on. Then set it to something, and what that something is going to be a list of rules. So options, image styler, and then you have a list where, let's say, option A has a default value of B, option B has a default value of C, and so on. So this is kind of what the options function is expecting. In this case, what we are doing is we are inheriting all the options of the image symbol. So image is a built-in symbol in Wolfram language. So if you have something like test image, which is the image we're working on, this is an image in Wolfram language, and that image symbol has a list of options. And what we want to do in this case is we want to say everything that is a valid option for image should also be a valid option for our image styler. So we are assigning the options of the image to the options of our function. And let's look at those as well, just to see what we are dealing with. So for images, there's options alignment point with a default of center, baseline position, color space, so on, so on, so on. So we want all of these options to also be valid for our image styler function. So this is what we do. Additionally, after defining them in a separate line, you need to include them in the arguments, because obviously people need to be able to define them themselves. So the way you do that is you have another argument called options, or technically called anything you like, but obviously for clarity, you can call them options. And this argument needs to be an options pattern argument. And again, options pattern is a specific type of object in Wolfram language, which is just a list of rules, a list of options and their defaults. And after you have defined them in your argument definition, in your function signature, you also need to provide them in the actual function itself by referencing the argument which defines them. So as I mentioned, a bit of a heavy syntax, but very useful. So let's see what happens. Oh, here we're defining custom options. Okay, so in the previous step, we inherited all of the options of image, but here we also want to provide some custom options as well. So we said that options takes a list of rules, and this is exactly what we have here. So this is our custom list of rules that we want our function to understand. We are adding a radius option, or an option called radius, and the default value that option is going to have is 2. But importantly, once we define it, users can override that default value if they choose so. We also have RGB values option, which defaults to 111, a list of ones essentially. So what we are doing here is we are joining our custom defined options with all of the options of image, and what that is going to give us is, well, a lot of options, all of the options of image and our custom ones. Finally, we can add a grayscale option to our list of options. And to do that, we'll introduce another helper function called grayscale, which takes an image. It takes a Boolean argument, and essentially the idea is if the user passes if the user passes true to this grayscale function, then they're going to receive a grayscale version of their image. So this is all that this helper function does, and we can actually include it in our options, in our list of options. So again, we have our radius, RGB values. Now we have grayq, which defaults to false. So if the user doesn't provide anything for grayq, then that is going to be false. And we can actually implement that functionality in our function itself. And again, we have options in our definition, and we have them here. And we are also checking for the grayq option. So our function is getting a bit heavy now. There's a lot of things going on, and we'll see how, in a minute, we'll see how we can break it up to be more manageable and more readable. So Christoph is asking, is there a common policy when to use strings and when to use symbols on the left-hand side of option rules? So radius 1 versus... Oh, okay. So Christoph is asking, when you are defining... Let's go back to our options. So when we are defining this option, let's say radius of 2, should we use a string like we do here, or should we have... If I go back, or should we have radius 2? Now, both of these are going to work in Wolfram Language, but I think the common convention is if there is a built-in symbol in Wolfram Language that is not a string, then use that. So in the case of radius, there isn't, which is why we use string. But there are things like, I believe, color. No, red. Yeah, so red, for example, is a built-in symbol in Wolfram Language. So let's say you wanted to use red on the left-hand side. Let's say we have an option here, red true, and if the user passes true, then we apply some red filter. So instead of using string in that case, because there is already a red symbol built in Wolfram Language, then we can just use that directly. And if there isn't, we use strings. I don't know if that is the official kind of policy or convention, but this is mostly what I have been going by. And I think, yeah, from my observation, that's usually the way it goes. So there are also things like image size. So you don't need to use a string. Again, not sure if that is the official way, but that's a good question. It's all about convention, because both the string and the undefined object is going to work, because after all, a string is just another object. But good question. Hopefully that makes sense. Yeah, not 100% sure, but that's probably a good rule of thumb to follow anyway. No problem. Cool. Let's test our latest function. So here, okay, this is interesting. So let's see what we are doing here. We're calling our image styler function, and now we're passing an option called image size. Now, if you go back to our option definitions, we didn't define that image size. So it's not part of our custom defined options, but it is part of the image options. And because we have inherited all of them, we can use it directly in our function. So image size is part of the options of image. Defaults to automatic. So if we don't pass anything for this, it doesn't do anything. But if we pass something like 40, then obviously it scales, or it resizes the image to 40 pixels wide, I believe. So the custom styles don't work yet because they are being fed directly into the image. So let's see how we can fix that. Here we're just cleaning up some of the options. So this is the new line of code that we have added here. So here we are saying, again, the syntax is getting a bit hard to read, but essentially what we are saying here is we are saying that if the options that the user has passed into options should be deleted if they don't follow, if they are not either radius or RGB values or grayq. And again, let's define that function, see what it does. So now that we are parsing our options correctly, our function is able to take all of the options for image as well as all of our custom options. So in the first case, we have blur, the blur style. We're passing the blur string as an argument of the style, and now we're including our custom options. So um, we're including the radius options, and we're saying 10. We can say 100. We can say 1000. Once we have an option that it's working, we can override the default value and we can pass whatever we want. Same idea for sharpen, same idea for RGB, and also for the last option we added, which is gray Q. Again, when we specify this option as true, obviously we get the grayscale version of our image, and if we leave it out, we are going to get just our image back because this is automatic, and we define automatic to basically do nothing, like accept this to be 1 1 1 and so on. Cool. So now we have, okay, let's see how far we have got into our function. Now we have a function that is able to take arguments that are restricted by head, and in some cases by predicates. We also have a function that is able to take image size. It's able to take arguments that are inherent to any images in Wolfram language, and it's also to take, sorry, not arguments, options. It's able to take options that are inherent to images in Wolfram language, and it's also able to take our custom defined options. Cool. So we have done a lot of work to kind of restrict the arguments to make sure that the arguments that go into the function are what our function expects, but we have done nothing to kind of restrict options now. So if the user passes some bad option, that goes through and it produces errors, which is hopefully not ideal. So this is what we're going to do next. So again, we're doing, I'm kind of glossing over this point because I do want to get into some more important concepts like overloading and things like that. So I'm not going to go through every line of the syntax. I'll just basically tell you what the code is doing as an idea and move on from that example. But here we're filtering options. So we are saying that any options that our image takes should either be our custom options, or sorry, should either be the options that so let me try saying that again. Any options that our image takes should be options of an image. Should be part of the options that exist for the image symbol in Wolfram language. Hopefully that makes sense. So that means that anything that is not part of the options of image will be filtered out. And the idea is to solve the problem that we saw in the previous slide, which is when a user passes a bad option, it shouldn't be accepted. Okay, so now we have now we're arriving to the last and probably really the most powerful way that we can restrict the arguments and the options of our functions, and that is the condition. So again, condition is a built-in function in Wolfram language. It has a shorthand, which is this /semicolon. So probably if you hover over that, that should tell you that it's a condition. Yeah. So how is condition used? So we can have, let me just play around with the spacing here so it's more clear what we are doing. So that's not going to work. So we have our function definition, which can be as complicated as we like. We can restrict by heads, we can restrict by predicates, we can provide default options, default values, we can provide options. And after we close our brackets of our comma separated arguments, we can have this condition shorthand. And everything that comes after condition is again something that can return true or false. Now, this is very similar to this blank question mark test, and the main difference is that the blank question mark text test is applied only to a single argument in your function. So here, if you have the style argument and you have some test for that argument is only applied to this. That test is only applied to this argument. But what if you want to have some test that tests all of the arguments via some, let's say, complicated or involved logic? Well, that's when condition comes into play, because once you're outside of your argument definition, you can call all of the different arguments. So this example is probably not the greatest because the condition actually just uses one of the arguments, which is option. So we can actually wrap this functionality here after we define our argument. But I'll probably go back to our simpler example. But let me just show you what this is doing. So as I mentioned, everything that comes after condition does some test, and that test returns either true or false. So what the test is in this specific case is we are testing whether the keys in the option. So when we pass an option, it is something like radius 10, and in that rule, the left-hand side is the key, and the right-hand side is the value. So key value pairs, again, very common everywhere, and the Wolfram language way of defining those is as rules. So when we say that we are checking the keys of the options, we are checking the left-hand side of everything the user provides. So if the user provides radius of 10, we're checking whether radius, which is the key, is contained in the options of image styler. Essentially, we're checking, is this an option that actually exists? Which is probably the most simple way to make sure that we're only accepting options that actually exist. So this is the only thing that we have added since the last time. But yeah, these conditional statements after the argument list can again be very powerful because you have access to all sorts of functions. Let's go back to our simpler function. And let's say we have, we can keep this and we can define some condition here just to kind of illustrate something more useful. What could we say? We can say that, we're reversing a string, so we can say that if the argument, just trying to think of what is a good example. String reverse. Let me write this out first. Test it. Then I'll explain what that does. Or let me just test it that it works the way I think it works. Yeah, so here we have a condition that is saying that that the function is valid only if the argument is not the same as the argument when it's reversed. It's a bit redundant. I probably should have thought a bit better about this example before I started, but the idea is that we have some condition here, and we're saying if the argument is already the same as the argument when it's reversed, then we don't need to go into the right-hand side because we have already accomplished that. So for a string like just a series of A's, they are the same. So essentially we are testing, let me do this. Essentially we are testing this string reverse, this, which evaluates to true, which makes our condition fail, which in this case makes our function undefined. But yeah, the important thing is if we had some other argument here, let's say we had some integer, in our condition we have access to both arguments. So we can have a different test for x, we can have a different test for y, and and restrict our arguments by some more complicated logic. That wasn't much clearer, but hopefully at least it's an additional example of what we can accomplish by conditions, because again, it's a very kind of powerful way of restricting our arguments. Let's move on here. Here we have slightly more complicated logic for the conditions. Aside from checking whether the user passed options are contained in the options of image styler, we can also have some additional tests. So here we have essentially comma separated tests. Here we are looking up specific options from those that the users may have provided, and we're saying that essentially, again, I'll just tell you what the code does without going symbol by symbol in it. We are saying that the gray Q option should have a boolean value, so either true or false. So if the user has provided gray Q, the actual value of this should be either true or false. So if someone tries to provide gray Q with value 50, then that's going to fail this test, and that's going to make the function undefined. Likewise, for radius, we are only expecting positive numbers. So if somebody provides radius goes to false, then that's not valid. We don't want to accept that. And likewise for RGB values, we want, again, our pattern of repeated 3 positive numbers. So simply we are adding a few more tests to make sure that we are filtering out any invalid options, any invalid option keys, which is what our first test does, and any invalid option values, which is what the next 3 lines do. Again, we can do some testing. Now, when we pass bad options and bad values, we just get the undefined function, which is fine. And now, even when we have valid option keys, if the value is invalid, we are again correctly saying that the function is undefined, and this is what this does essentially. So we did this. So if I go back here, we are looking up. We have tests for our custom options. So gray Q, radius, RGB values are our custom options. So we're handling those very gracefully now. We are essentially undefining the functions if either the keys or the values are invalid. But if we have invalid value for some of the options on image, such as color space, then this still produces an error. So you can go, obviously, how deep you can go into kind of making sure your function robustly handles all sorts of bad input really depends on how important that function is, and probably even more crucially, how many people will be using it. Because if you're working on some project for a client, for example, then it's very important that your function is robust, it handles errors gracefully, it produces informative error messages, which we'll come to in a minute. But if you are just writing a function for yourself to do a few things, then you probably don't need to go into that much level of detail, even though it is still a good practice. But yeah, you can. Essentially, the idea here is you try to anticipate all the different kinds of bad input that can go into the function, and then you handle those preemptively, and you handle those in kind of reasonable ways. So yeah, instead of going into every single option in the options of image and try to handle every single bad input that can go into them, for now we'll just leave it. But the important thing is that if you did want to do that, you could, of course. So let's get into some more kind of important high-level ideas. So overloading is probably the most important. Once we get past the basics of a function, providing arguments and restricting arguments, overloading is probably the concept that is going to help you the most. So what is overloading? Well, as we mentioned, our function, even though it's quite capable now and it handles quite a lot of errors, it is getting a bit cumbersome to read. We have the switch statement that checks all different types of styles that the user can pass, does different things based on them. We're filtering options, we're providing options, and so on. So a way to break our function up is to overload the definition with different arguments. So what do we mean by overload? So overloading is defining the same function. So in this case, image styler. So we are defining it multiple times. Each time we are defining it with different types of arguments. So in this case, we are defining. So let's see how that looks like in practice, because it's probably easier to explain it that way. Here we're defining image styler that takes an image, takes some options, applies some conditions to that option, and in this case, we are checking whether the user has passed a grayscale option. So this is what this test does, and whether that is Boolean, obviously. If the user has passed a grayscale option, then we apply the grayscale function. This is our custom defined function. We're applying that to the image. Next, we are saying, so here we're providing an automatic style to the style argument. So if the user calls the function with an image, but without a style, then we just assume automatic. Then we can define the same function with a blur again. So the basic idea here is that you have multiple definitions on one function, and based on which definition the user input matches, that is going to do. So you can see, you can look at it as an alternative to the switch statement. So previously we were we had this switch statement that checked whether let's say the second argument, the style argument, matched a specific string. Now again, that becomes cumbersome, because you can imagine you can have, let's say, 10 different styles. If you were to write a switch statement that matches 10 different things, it quickly gets out of hand. So instead of doing that, you can have a separate definition for each of the styles that you care about. And again, that also helps with handling bad input, because in this case, if you have defined your function with all of the values that you accept, that means that if the user passes any other value, then none of the definitions are going to match. So they're going to receive an undefined function. So yeah, the whole idea behind overloading is that you are overloading is in relation to the definition of the function. So we are overloading the image styler with all sorts of definition with different input. And that is very useful for breaking up your function into what are essentially several mini functions, even though they share the same name. So we do that with, again, instead of using switch statement on the style, we can define an image styler definition in which the second argument is blur. Again, we have our typical filtering conditions here. And now the right-hand side of each function is much more simple, because we are saying when the second option is blur, obviously the only thing we need to do on the right-hand side is apply the blur. Obviously, make sure the options are valid and so on. Likewise with sharpen, if the second argument is sharpen, then we only need to apply sharpen and so on. So you can see that we have gone from one monolithic function into 1, 2, 3, 4, 5 different definitions on the same function, and functionally that is still the same. So as far as the user is concerned, they can use the function the same way, even though you have defined it 5 different times with 5 different arguments. It is still the same function. It is a function with the name image styler, so a person can just call it. They can pass the image, they can pass the blur argument, and that means that when a user calls this, what is going to be called is this specific function. So yeah, that makes it much easier to maintain, much easier to document, much easier to read, especially if you're reading other people's code. You can kind of inspect each specific overloaded case on the same function. Cool. And again, we're doing some testing with invalid input just to see if our function is still able to handle that and return unevaluated, which it does. Recursive and iteration. I do want to. I think I'll come back to this because I do want to get into error messages as well and to upvalues as well. So if I have time, I'll come back to recursion. That's probably slightly beyond the scope of this webinar anyway, but maybe we'll have time to come back to it. One thing I want to go through before I go into error handling and error messages is upvalues. So upvalues are, again, another concept that can be useful, although while overloading functions is very common, you see it in all sorts of Wolfram language code. You can use it as long as your function does different things based on different inputs, based on different arguments. You probably can and should overload it with different definitions. So upvalues, on the other hand, is a concept that is a bit more situational. It's a concept that you see less frequently, I would say, but it's still a useful concept to kind of be aware of, just in case it's ever useful to you. So what upvalues are is, well, you can think of it as I'm not sure if that's technically true, but you can think of it as a special case of overloading. But in the case of upvalues, you are providing another definition of your function that is only executed when your function is wrapped in something else. So let's look at an example because it's a bit difficult to explain otherwise. So here we are operating on our image styler function, and we are using this special syntax for upvalues, and we are saying essentially when the image styler function is wrapped in information, do this on the right hand side. So when the user passes our function into another function, in this case information, but this could be anything. It could be any Wolfram language function, it could be any custom function. In this case, it's information. I want to say when the user basically calls that, this is what we should return to them instead of trying to match any of the previous definitions of our function. And that's very useful. I think information is probably the most useful upvalue, at least that I have encountered in my code, because it's a bit difficult to think of when do you want to act differently based on when your function is passed to something else. It's kind of difficult to think about and predict, but information is a very obvious one. So if somebody requests essentially information of your function, you should provide them with the list of options formatted as a data set. So it's kind of an obvious one. Just trying to think of when else have I used upvalues. Nothing jumps to my mind. If you have used upvalues in your own code, feel free to share because I'm kind of curious. Yeah, can't think of anything at the moment, but information is an obvious one, and it's just a way. Again, it's another definition of our function, but in this case, it's in the special case when our function is called as an argument to the information function. As I said, a bit situational, but useful to be aware of, because even if you can't think of anything now, it's useful to know that if you come across that case and if up values are relevant, then you remember that part and you use them. Cool. So, Erhan, let me see how much time I have left, just to make sure. Okay, so we have about 10 minutes left, which means I will be able to cover error handling. As we mentioned earlier, the most simple and fairly graceful way to handle bad input is to simply return an unevaluated function or undefined function. And again, that is the Wolfram language way of saying the function with the arguments you have provided is not found, is not defined, doesn't exist, basically. And that's a fairly clear message to the user that they are trying to do something that is not supported. But obviously, we can be more explicit than that. We can provide, well, first of all, we can do tests in our function itself. And if these tests are violated, essentially, we can provide custom messages. So instead of returning an unevaluated function, we can return something more specific, like saying, hey, you should have provided an image here, but you didn't, and things like that. So let's see how we actually do that. There are a few concepts to introduce here. Let me just have a quick look. Yeah, so we get to messages next. Okay, so let's see what we're doing here. So here you see a few different built-in Wolfram language functions used. The main ones that we want to focus on for this example are enclose and confirm quiet. So these are usually paired functions. So every time you see enclose, there will be some sort of confirm inside the enclose. In this case, it's confirm quiet. There's also confirm by. Quite a few different confirm types of functions. But let's talk about what this does in general. So when we use enclose, we are obviously enclosing some code inside of that, and we are saying, and for part of that code, we want to confirm some condition. So in this case, we're enclosing this grayscale logic in our enclose statement, but we're only checking this part, the part that is in confirm quiet. And what that does essentially is it confirms that whatever goes inside doesn't produce any messages. That's why it's confirm quiet. So essentially, meaning in this specific case, that if the user passes an option that is not in the options of image, this piece of code is going to produce a message, and that message is just going to come from the built-in Wolfram language functions, most likely from image. So when when a message is produced from this piece of code, that message violates the confirm quiet test, which means that which immediately sends a message to enclose saying stop the evaluation now and return something. So if we take it step by step, let's say we pass some option here that is invalid, like in this case, actually with the testing of the example. Here we pass a valid key, but not a valid value. So when that goes into our function, it goes into confirm quiet, and it goes into this image function. This bad color space value is going to make image complain. It's going to make an image produce a message saying, hey, this is not a good value, blah, blah, blah. When it does that, this confirm quiet immediately signals to the enclose function that that there has been an error inside confirm quiet, which means that everything else in the enclose is not going to be evaluated. So typically in Wolfram language, every time you have an error, evaluation continues, it tries to continue later on. So there's no there's no crashing of the whole workflow if you encounter an error. So enclose is one way to kind of prevent that. We are saying that essentially in this case, this line of code will only ever run if whatever is in confirm quiet doesn't produce any messages. So a bit difficult to explain, but hopefully that makes sense. You're ensuring that something is the case before you evaluating the rest of the enclosed code. And if it fails, we are replacing the failure. So enclose is going to return a failure object, which we don't care about in this example. So we are replacing the failure that enclose returns just with our image. In practical terms, that means that when we pass a bad value, confirm quiet is going to be tripped. This is not going to get evaluated. Enclose is going to produce an error, and replace is going to replace that error with our original image. From the end user point of view, you just get your default image back without any styling, without any errors applied to it, and so on. Cool. Oh yeah, there are some bugs in image size which unfortunately still haven't been fixed, which allow some bad values to seep through. But these are mostly bugs with the image symbol in Wolfram language rather than our custom function. Finally, we can talk about error messages. And thankfully, the idea here is much more simple than some of the things we have been discussing. So once we have our function definition, let's say, keyboard stop working for a second. Let's say we have a function that does something. The way to define error messages on that function is with this double colon notation. Not the number. You give a name to your message and you give the actual error message. This should be a number. And this is all you need to define an error message. And then once you have this error message, you can call it from inside of your function based on some conditions. So here I can have numeric q, I believe is the function x, and I can wrap it in an if statement, and I can say if the argument is numeric, square it. If it's not, we can return the error, and so on. So this is a fairly simple idea, and here we're defining quite a few error messages, not an image, not a style, that we can then apply to our function. And I'll just show you how to actually call the error messages from the from inside of your function, and that's probably going to be it for today. Again, because our function is getting a bit bulky, it's a bit hard to see, but this is the relevant line here. We are doing some tests, and based on, we're trying to identify the specific error, and once we find that the specific error is not an image, then we simply return this message. So inside of message, we simply specify the specific error that we want to return. In this case, it's image styler bad image option, which is bad image option is this. So essentially what the user is going to see is this piece of string. I'm pretty sure there's some, oh, this is much more clear because this is in one of the overloading ones. So yeah, here we have a simple definition of our function, again, using overloading. We have some condition. Basically, we're saying if the first argument is not an image, just execute this. Basically, return the error message and return the original image. Pretty sure there's some testing, so you can see what that looks like in practice. If we try to pass bad image, we get this custom error message now saying bad image is not an image. The only other thing I wanted to mention is that you can have these string templates here in your error messages. So here, one is actually a slot that you can put whatever into it. And the way to do that is if I go to one of these messages. So if you're calling a message that has these string slots, you can provide a second argument to the message function, which will get inserted into that string slot. So if you have too many arguments, you can be specific about it with the user. So you can say at least one of these has an invalid option value, and so on. So I believe this is it. There are a few other things in the notebook. Again, if you're interested in any of the specific concepts, such as options, error messages, argument restrictions, I encourage you to look at the extra notebooks that are in the notebook materials for today.